principle, you could reconstruct it from the notes and stuff. But what I'm going to do in this last part is just to give you a kind of flavor of something called structural Ramsey theory, which connects to ω-categoricity and to Ramsey theory in the way that was described by Isabel and Stone. So before we get started, are there any questions that you would like to ask about what we've done up to this point? All right, so I want to tell you about what it means for a class of structures to be a Ramsey class. So we're going to have L.
May I please raise your voice?
Sorry?
Voice. Can you please raise your voice?
Oh yeah, sure. So we're going to have L, which is a finite relational language. So just recall, this means that we have some finite number of symbols, like less than, or like a graph relation, or whatever. So we have a finite relational language, and we're going to have K, which is a class of finite L structures. And let's remember what this means. This means that we have a finite set together with interpretations of those relations. So if we have a single binary relation, then maybe we could have finite sets, and we interpret the relation on those finite sets so that it's an order, for example. Or maybe it's a graph, something like that. So we're going to have a class of finite L structures, and we're going to assume, for purposes today, K is a Ramsey class. Does anyone remember what that means? Yeah.
Okay, so it's a, well, first of all, non-empty class of finitely generated structures.
Yeah.
So it has the hereditary property.
Yep.
So any substructure of structure is there, and the joint embedding property. So any two structures can be embedded in a bigger structure within the class, and the amalgamation property. So so you can amalgamate any two structures over a common substructure.
Yeah, exactly. So let's just remember that you have HP. So this says if I give you A, which is in B, B is in K, then this implies A is in K. Then you have J, which says A is in. What's up? No, okay. So J says if I give you two things here, then you can put them in C. And AP says if you have A, and you put it into B, and you put it in C, then you can put these both into something, I don't know, let's call it D, where the B and the C embed into a way that A gets glued. Okay, so this is something nice, and what's the point of thinking about Ramsey classes? Well, the idea of Ramsey classes is that if you have K, a Ramsey class, then you can associate to it a limit. So it has a Ramsey limit. So we have F, which is sometimes called F lim of K. So this is the unique uptisomorphism countable structure, which has age K, so all of its finitely generated substructures live in this class, and it's homogeneous, so lots of automorphisms. So this is the unique countable L structure with age F equal to K, and F is homogeneous, or ultra-homogeneous, whichever you prefer. Okay? And that meant that it had a really big group of symmetries. Now the reason that this is interesting is it's sort of analogous to, I don't know if any of you have taken like a Galois theory class, but Galois theory sort of says, fields are hard, groups are easy. Wouldn't it be nice if we can translate field theoretic questions into group theoretic questions? It gives you this algebraic bridge to go from field theoretic questions to questions in groups, which maybe you can solve by translating into that language. So if I give you a big bunch of finite structures, which maybe are combinatorially complicated, you want to associate some kind of infinite limit object and study it by thinking about its mini-symmetries. So in a way, it's very tightly analogous to what happens in Galois theory. I give you a big bunch of things, like let's say finite linear orders. Finite linear orders have how many automorphisms? If I hand you a finite linear order, how many automorphisms does it have? Yeah, a finite number, yes. You could do better than that. We have a lot of lazy bounds, you know, like, it has exactly one automorphism. Why? Well, because it has the least element. Every automorphism has to take the least element of the least element. So the least element is fixed. And then it has a next least element. And the next least element has to be preserved by every automorphism. So that's fixed. And then it has a next least element. And that has to be fixed. And everything is either the least element to the next least element to the next least element. You know, eventually you exhaust the whole thing. So finite linear orders have no automorphisms at all. So the automorphism group is not helpful. But if you assemble them into some infinitary limit, you get the rational order. How many automorphisms does a dense linear order, a countable dense linear order with no endpoints have? Does anyone have a guess? Yeah?
I'm guessing as many as the rationals, at least.
Probably more.
Certainly as many as the rationals, because the rationals act on themselves by translation, right? So you can shift by any rational number. So at the very least you have that many. Do you think it's countable?
Yeah.
Yeah. Okay, in this case it has a nice continuum. You have one for every real. So I think that is a nice exercise. So for those of you that have thought about such things before, prove that the automorphisms of the rational numbers as a dense linear order, not as a field, just as the order, this has size continuum, 2L0, which is, by the way, the size of the reals. But maybe the way you should think about this is 2D0 is this set of sequences of links, you know, countable linked sequences of zeros and ones. So you need to find a way of associating to each countable linked sequence of zeros and ones some automorphism of the rational order. And if you think about it that way, then it's maybe not so hard. Like break up the rationals into a countable bunch of pieces, and then you can sort of independently choose what you're going to do on those pieces, and that's going to give you continuum in automorphisms. But okay, that's a hint. Anyway, so
can you do that express thinking? Like every cut you can use cut to
maybe, but it's not obvious to me that counting cuts is going to immediately give you. Anyway, I leave it to everyone to think about this problem. So okay, so. So there are a few things that I need to tell you. So always, if M is a countable L structure, okay, I'm going to assume countable. What I'm going to say actually doesn't need that. The automorphism group of M, it's a topological group. It has a topology on it, which is compatible with the group operations. So it's a topological group. With the topology given by a basis U A bar B bar, where these are the automorphisms sigma in on M, such that sigma A bar equals B bar, where A bar and B bar are same length, finite tuples from M. Okay, so we imagine that we've got some N here, and I take some points, let's say A0, A1, A2, and then I've got some other points over here, B0, B1, B2, and I look at all the automorphisms that send A0 to B0, A1 to B1, and A2 to B2, and I declare that that's an open set. So this is like saying, if you can specify finitely much information about what an automorphism does, I tell you how it acts on a finite tuple, and the set of automorphisms that agree on that behavior form an open set. And this gives you a topology for the group. And so the overarching theme of Frisé theory is you want to translate interesting model-theoretic, structural, combinatorial questions about the class of structures into topological questions about the automorphism group. And the theorem I'm going to talk about today is going to be a sort of maybe the most striking application of that form of thinking. But it turns out that in the case of a Frisé limit, the automorphism group as a topological group completely determines the structure. So it encodes all the information. And so it gives you a perfect translation from model theory world into the topological group world. So this is sort of relevant background, but I told you I was going to tell you what a Ramsey class of structures is. So we say K is a Ramsey class. If whenever I give you A, B, and C, which are in K, there exists some D, which is in K, such that, sorry, I made a mistake again. So for every A, D, and K, and R in the natural numbers, there exists a D, such that D arrows B, A, R.
Clear.
It's perfectly clear, right? Okay, so this notation, it looks awfully familiar, right? So, in the context of the Arrow-Schrader arrow notation, what was here at the top, at the superscript? What did this correspond to?
Okay.
K, it was K, and what was K?
So structure is on
Yeah, this has the subsets that were colored. And R corresponded to what?
number of colors.
Number of colors. B was what?
The monochromatic set we want.
The monochromatic set we want. And D was what?
The entire set.
Yeah, the set of individuals, the size we needed in order to be guaranteed a monochromatic set like this. Okay? So now you've noticed that I've got the same shape, but instead of talking about numbers, I'm talking about structures. A, B, and D are all structures. So what in the world could this possibly mean? Now, what it means is the following thing. So what it means is, so we have to give some definitions. So MAB is the set of embeddings from A to B. So let's get an example. So let's say A is less than B. I'm going to think about this as a two-element linear order, where the elements are A and B, and A is less than B. And I'm going to take C to be C is less than D is less than E. Okay? Why did I do C? I'm going to do B. Okay, so now let's describe MAB. How many elements does it have?
3.
3? Why?
A goes to C and B goes to D.
Yeah, so I can draw the picture here. I've got A, and I've got B, and then I've got C, D, and E. So this is my B, and this is my A. And now I have to ask the question, how many choices do I have for where A goes?
2.
2. So A can go to C or to D. If I send it to C, then I get 2 choices for where B goes. Namely, I can send it to D or to E. But if I send A to D, then my choice for B is determined. I have to send it to something bigger, because it needs to respect the relation. So it's got to go there, and that gives me exactly 3. Does everyone see that? So there are exactly 3. So given that I have the order relation like this, there are 3 ways of mapping A into B in a way that preserves the order. Of course, there are a lot more functions. So this winnows down the collection of functions. There are a lot of functions from A to B, but only 3 of them respect the order, which is what we care about. So we want an injective function that respects the relation, and that requires, there are only 3. Does everyone have some sense of what this is? So we think about the embeddings as ways of putting a copy of the structure A into the copy of B. So inside of B, I've got 3 copies of A. There's this one, there's this one, and then there is this one. So 3 copies of A living inside of this set. Then sometimes we write B choose A. This is the set of substructures C inside of A. Inside of B, such that C is isomorphic to A. Okay? So, in this case, notice that if I also asked what is B choose A, it would have been the same answer. It would have been identical. So, can anyone come up with an example where the embeddings are different than the isomorphic substructure? Adam?
I would change the structures to not be rigid.
Yeah?
So I would choose graphs. So there you would have the embeddings are different than copies of the field.
Yeah, great. So let's try graphs. So here we're gonna have a complete graph on 3 vertices. So let's call this B. So here we've got X, Y, and Z. And then I've got A. So let's say this is A and B, and they're connected by an edge. Okay? So now the question is, how many embeddings do I have from A to B?
3.
6. Yeah, now it's 6. Why? Well, because it's actually any injective function from here to here will work, because I can send A to X and B to Y, or I could send A to Y and B to X, right? So the image will be the same, but the actual function will be different. And what we see is that the difference is that there's an automorphism of this structure. Namely, I can swap these 2 things. And so even though they have the same image, they're like different functions that can be the same, right? So in this case, I have this is the same substructure, but there are 2 functions. One that takes me A to B, or sorry, A to X and B to Y. Another one that goes A to Y and B to X.
That doesn't preserve order like you said.
Yeah, but here the structure is a graph. So there's no.
It's a different structure.
Yeah. So here I have an order. Here I have a graph. The order is rigid. It has no automorphisms. And here I do have automorphisms, and that increases the number of ways that I can map. Okay. So an observation, which is sort of implicit in what was being said earlier, is that if A is a rigid structure, I don't know. In Egyptian, I guess you say rigid. What this means is that odd A is equal to 1. So it has no non-trivial automorphisms. The embeddings of A into B they can be identified with the copies of A and B. Because if you have no automorphisms, then once you know the substructure, you know exactly how to map it. There's a unique way, which we saw in this case. Right? Cool. So I still haven't told you what a Ramsey class is. So but we're building up.
In general, the equation is you multiply with the cardinality of the automorphism.
Yeah, exactly. So that's even maybe a better thing to say, which is that the cardinality of the embeddings of A into B factors as the cardinality of the automorphism group of A and the cardinality of B choose A.
So in rigid case, this is 1 in rigid. Okay.
Yes. So exactly.
What's this double-headed arrow?
What?
Cardinality was 2 cardinality errors.
Yeah. Do you know this joke about like
No, the
Serge Lang?
double-headed arrow between embedded A and B and B choosing.
1 to 1
To the right.
Which projection? Double arrow? No, right?
Oh yeah, I just say it was sort of informal, saying that there's a bijection. There's a correspondence between these 2. Yeah, no, but there's a joke about Serge Lang that I heard once, which is that he was a real stickler for notation. I don't know if people know that Serge Lang wrote like a lot of textbooks. He was a famous mathematician at Cairo. And so someone who was kind of just trolling was talking about some complex number xi. This is a capital Greek xi. But then they looked at xi over xi complex conjugate. You know, and you want to have a seizure when you see such a thing. Yeah. Anyway, so back to the story. So I want to tell you what this statement means. So what it's going to mean is for every coloring of C, every coloring C, which associates to each embedding of A into D, which is valued in R-1 colors, there exists some alpha, which is an embedding of of B into D, such that if I look at for every beta, which is an embedding of A into B, if I look at the coloring of alpha composed with beta, what I really mean is that there exists some L star such that for every beta in the embeddings of A into B, C of alpha composed with beta equals L star. Now this is miserable. You know, like Ramsey's theorem was hard enough. And now things are much harder. So I want to also give sort of an equivalent version, and then we're going to try to make this intuitive. So assume A is rigid for a moment. Okay, so it has no automorphisms. Then embeddings are the same thing as copies. Like it's this substructure. So then this is equivalent to whenever you have a coloring of copies of A in D with R many colors, there exists some B prime, which is a copy of B living inside of D, such that C restricted to the, well, I guess I actually need that A and B are rigid. Like everything is rigid, just for simplicity. So, I mean, I only need A and B, but whatever. We're actually going to assume the whole class is rigid elements. So, when I restrict C to copies of A living in B prime, this is constant. Okay? So let's draw a picture and see what this is. What? No. So, here's D. Now, the objects that I'm coloring, instead of K-element subsets, are now copies of A living inside. Okay? So I've got my big structure T, and inside of it there are maybe many copies of A. So think for a moment, like maybe D is a linear order with 16 million elements, and A is like the 2-element linear order. So I could take any 2 elements there, and that would be a copy of the 2-element linear order living inside, right? So it's got lots of them. And now, the thing that I want is I want a copy of B such that B lives inside of here. Okay, so yeah, so I guess maybe I should use colors. So, you know, the copies of A living inside of D are given colors. So this is like given by my coloring. Okay? Now what I want is something that looks like this. I've got a copy of B, which is some other structure, and inside of it, all the copies of A get the same color. So what I would really like is a picture like this. Okay?
Inside B.
Yeah. I would love this to be, well, so this is sort of my abstract goal. And what the Ramsey theorem says is if I find a D which is big enough, there is a D that's big enough, such that no matter how I color all the copies of A living inside, I can find a copy of B, which we're going to call B prime, isomorphic to B, where all the copies of A living inside of B get the same color. Okay? Now, when I'm dealing with rigid elements, I can really draw the picture this way. If I'm not dealing with rigid elements, then I have to think about embeddings, where I don't think just about the copy living inside, but rather the homomorphism, I mean the embedding itself. But I don't want to do that. So I'm going to assume that I'm working with rigid elements, and that will be justified tomorrow. But yeah, is at least the vague picture clear? So in this case, you know, A would be like the little n, or sorry, A would be like K that we had before. B would be like little n, and D would be like the capital. Okay. So we say that it's a Ramsey class that satisfies this property. And the kind of shocking and astonishing fact is that this property can be characterized purely by talking about the automorphism. So, Isabel, when am I supposed to stop?
We started at 45, so we have half an hour.
Okay, but all right. So I might not take all the time because I'm sure people will.
Exactly.
Go home. But yeah, okay. So here's the definition. Another definition, which is suppose G is a topological group. So it's a group with a topology on it, that's compatible with the operation. Then G is called extremely immutable. If whenever G acts on a compact space X, so I'm talking about a continuous action in this case, compact space X, then there is a fixed point. i.e., there exists some X star in X such that G dot X star equals X star for all G. So you view G as living inside of, acting by homeomorphisms of the space X, and then it has to fix a point. Okay? So the thing to notice about this is that this is what's called a dynamical property. So dynamics is the study of group actions, especially in the continuous setting. And what this is saying is that you've got this property of the group, which is talking just about the dynamics. It's about the way it acts on topological spaces. And the theorem that I want to tell you about says the following thing. So this is by Kekris, Pestov, and Zorchevich. This is called the KBT correspondence. It is. Says, suppose K is a Frisé class with Frisé limit F. Then K is a Ramsey class. So it satisfies this kind of structural version of Ramsey's theorem. If and only if one, oh, no, sorry. Is a Ramsey class consisting of rigid elements the structures in the class have no automorphisms, if and only if the automorphism group of F is extremely mean. So this should be really surprising. This statement is about combinatorics. It's about colorings of finite substructures. This is about dynamics. It's about the topological group actions of some infinitary linear. And the theorem tells you that these two things are the same, which is shocking. So in the last few minutes, what I want to do is I want to explain just a small part of this. So I want to prove that if odd F is extremely amenable, then K consists of rigid elements, which is really a small part of the theorem, but it's going to give you some hint in how this goes. So the thing is, to use extreme amenability, you need to get this automorphism group to act on something. It needs to be acting on a compact space to use that property. So a natural question is like, what compact space we're going to use? How are we going to cook up a compact space in which this is acting, so that we can leverage extreme amenability? So let me show you that part, and then I'll sort of gesture at the rest, and then we'll call it a day. Why does odd F being extremely amenable imply F consists of, K consists of rigid elements? Okay, this is a question. So we need a space on which to act. Now, I'm going to define a space called LO of F. So this is the set of linear orders on F. Now, how do I specify a linear order? What is a linear order? Well, a relation in model theory is determined by telling which pairs are in the relation, right? So we saw in Dowd's lecture that the interpretation of relation is just the set of, if it's an inner relation, it's a set of intuples in which the relation holds. So to specify a linear order, I need to tell you which pairs are in the relation, and and then it follows which pairs are not in the relation. So I can think about LO of F as being living inside of 2 to the F times F. So F times F, these are pairs from F. And when I write 2 here, what I mean is 0, 1 value, functions which take values 0 and 1, whose input is a pair. So I'm going to think about a linear order as living inside of here by giving me the characteristic function of the relation. So with this identification, I can view this as a subset of this space. And I'm thinking about this as a topological space in the same way that Christian was in his lecture when he was talking about 2 to the omega. So 2, the 2-element set, I can think about that as having the discrete topology. And this is a big product, countable product, of a set with a discrete topology. Finite sets are compact. So this is a big product of compact spaces. And I don't know, do people here know Tikhonov's theorem? So it says that a product of compact spaces is compact. So this is compact as a space. I mean, it's not very difficult actually to prove by hand, as Christian was mentioning. This is a compact space. So this is compact. It's also a nice exercise. So if you think of the space of linear orders living inside of 2 to the F times F, it's closed. Okay? So I'll give you a hint about how this goes. So how do you say that something is not a linear order? Well, the axioms for linear order say what? It says that it's a relation which is symmetric, not symmetric. It's a relation which is reflexive, anti-symmetric, and transitive. Now, if you say, for example, that something is not transitive, what does that mean? It means you can find a triple such that the first pair is in the relation, the second pair is in the relation, and the third is not. You'd see that behavior on 3 elements which is the same thing as seeing that behavior on 3 coordinates here. So anything that agrees with the bad example on those 3 coordinates will be not a linear order. So like the counterexamples to transitivity on those 3 elements form an open set. And then if you take the union over all 3 elements which could possibly give you transitivity, that's going to be an open set, because it's a big union of open sets. And so you can do something similar for the counterexamples to reflexivity, the counterexamples to antisymmetry. And what you can prove is that the set of non-linear orders is open, because anything that involves specifying what happens on just finite many coordinates describes an open set. And then so you get the complement of that, which is the space of linear orders, is closed. Okay? And what do you know about closed spaces inside of compact sets?
They're compact.
They're compact, right? So the space of linear orders viewed as a closed subset of this compact space is compact space. Moreover,
So
Yeah.
LOF is linear orders on the underlying set of the structure, right?
yeah, that's right. So there's no relation with the rest. It's just a set of linear orders. Okay. Moreover, sorry, let me switch colors. So moreover, odd F acts on LO. So suppose I take some linear order in F. I need to tell you, and I take some sigma in odd F. I need to tell you how sigma moves the automorphism. I mean, it moves the linear order. It's going to scramble the linear order in some way. And how do I tell you how to do that? Well, you just say sigma. So I need to tell you how this, whether or not, for any elements of x, whether or not this is true. And this will be true if and only if sigma inverse of x is originally less than sigma inverse of y. Or equivalently, I can, this is equivalent to say that x is less than y if and only if sigma of x is sigma dot less than sigma. So this is for all x and y. So in order to tell you what the linear order sigma dot less than is, I just need to tell you which pairs it declares to be less than, in that relation. And the point is that you look at the elements that are in the relation less than, and then you just push them forward by sigma. And that gives you the new relation. So the idea would be that you just take, so if you think about this relation, the arbitrary linear order that we took is a set of pairs, you just apply the automorphism to each one of those pairs, and that gives you a different linear order. And that's what we call sigma dot less than. So sigma maps less than to sigma dot less than by applying sigma to each pair in the relation less than. Okay? So I start with linear order, I apply an automorphism, it scrambles and gives me some other linear order. Okay? So, good. But now, let's assume that the automorphism group of F is extremely meaningful. So, we've got the space of linear orders. It's compact. It's acting on it. So, it's got to have a fixed point. So,
fixed linear order.
if odd F is extremely unequal, there is some special linear order, which I'm going to write less than star, which is fixed by automorphisms. By odd F. So it's what we would call an invariant linear order. But ω-categoricity tells you, so for say limits, in the context that we're working, are because I assume the language is relational. Finite relational language. So, because f is ω-categorical, if less than star is fixed by odd f, then it is definable. And something we haven't really talked about, but I'll just gesture at it. I can say it's definable by a quantifier-free formula. Why? Well, because for say limits eliminate quantifiers. It's part of the definition. I mean, part of the Freycius theorem, at least in the context of that we're working. So for say limits will eliminate quantifiers. So if A is in K, then A inherits a linear order from F, since A is necessarily in the age of F, which is K. So if you have a linear order on a structure, then that induces linear order on all the substructures by restriction, right? Because it's given by quantifier-free formula, so it also is a linear order on that substructure. But if you have a linear order on a finite set, how many automorphisms does it have?
One.
Only one, the trivial one. So this implies that A is rigid.
So all of this just to say that there is a definable linear order on the structure.
That's right, that's right. Well, in particular, it's by quantifier-free formula, so it passes to that.
Why do you why do you need it to be quantifier-free?
Well, because if I give you a formula, which is a linear order on a big structure, it might not be a linear order on a small structure.
So you need it because of the
Yeah, because I want to say, I mean, the idea is like A is in the age of F, so it embeds into F. So it's isomorphic to its image, and its image is a substructure. But I need to know that if I restrict the relation to just A, it's a linear order. And like in the language, right? Like obviously, like abstractly, I know that it's linear order. But how do I know that A itself, just as an individual structure, doesn't have the automorphisms? But in this case, I mean, okay, it doesn't really matter that it's by quantifier-free formula because we can just think about ultra-homogeneity. So I have A, and I might as well assume that it's living inside of F. Now, if A itself had a linear order, if A itself had an automorphism, I could scramble A by an automorphism, and that would extend to an automorphism the whole thing. But and because it's an automorphism the whole thing, we'd have to preserve the linear order. But then it would fix A, and that means that automorphism on A would have to be true. So you don't really need quantifier-free here. It's just a kind of stopgap. Does this make sense?
They are equivalent.
Yeah, it's equivalent. Yeah, it's equivalent. I mean, ultra-homogeneity is how you prove quantifier-free. So, but this is giving me rigid. So now, maybe just a final word. How would we do the same kind of argument to get from extremely amenable to the Ramsey problem? This is a much more delicate thing, but the idea would be that we translate from trying to find a D, like this. We do exactly the same argument that we did at the beginning of today, to translate from finding a finite thing to finding a coloring on the infinite thing. So now we suppose that it fails for the finite, and we use an ultra product argument to pass it to the infinite version. Then this, we suppose that this is, we suppose we're given a coloring, so we suppose we have some coloring, which is on the copies of A living inside of F with R many colors. Okay? And then we can view C as an element of, let's say, 0 to R minus 1 raised to the power F A. So, what is this kind of thing? It's a function going from here to here. So this is a big product space. And what I'll notice is that ought F will act on this product space. 0 through R minus 1, F of the A. So You scramble F, so you scramble the copies of A living inside of F. So you scramble functions going from the copies of F, A living inside of F to this finite set. And then what you do is you have this particular coloring, let's call it C0. Then what you do is you look at the orbit of C0 and you take its closure. This is a compact space. Because it's a closed subset of this compact space, because I took the closure. And that means that G is acting on this, because it always acts on the orbit, then it has a fixed point, and then I go from the existence of that fixed point to finding the thing. Now this is like a much more complicated argument, so I'm not going into all the details. But the point is that F will act on anything that I build out of F. It acts on the copies of it acts on linear orders that I put on top of F, it acts on functions that I build out of F, and using that I can find lots of compact spaces in which I act, and knowing extreme immutability is extremely useful for understanding the common theorems. And the remarkable thing is you can reverse the theorem, and this gives you a way of proving extreme immutability as well. But I think I'm going to stop there, so thank you. And maybe before we move on to questions, I just want to say that I know locally, Daoud and Isabel have been doing like a ton of work to make this possible. So let's just thank them one more time.